There we go. We're live and we're on air. Please feel free to swear if you want.
Is this my 15 minutes?
This is your 15 minutes. And then
I've always wanted to be a TV star, but I had more of a face for radio.
Physics, eh? Physics and relativity.
Yep.
I should say I'm obviously Darren, and you're Darren too. So it works very well. Right. So we spoke earlier, and you wanted to know about relativity.
Yes.
Which is a great thing, a thing that lots of people have heard of, and a few people do understand. It's one of the last, or it was the last major advance in what's known as classical physics.
Okay.
Okay, so there's classical physics, and then there's quantum physics.
Okay.
And this, I'd say, relativity, Einstein's relativity is a classical theory of physics. So it doesn't talk about fundamental particles. So the history of it, I quickly went through some notes. The history of it is that starting with Galileo, who was the first sort of major scientist to do experimental science. So prior to Galileo, you had people like Aristotle who would come up with physical laws based on a priori reasoning. So based on armchair reasoning, would come up with physical laws and say, things fall to the earth because it's their natural place, and they try and move towards their natural place. Things like laws like that, and up until Bruno and then Galileo, you had a few what you might think of as observational scientists who would observe some physical event or observe the heavens and hope some physical event happened.
Sounds like me.
Yeah, exactly. So, well, I mean, if you look at astronomy, obviously you can't do many experiments in astronomy. Yeah, you have to look at the sky and hope that the thing you think should happen happens. Then you can make some data. But sort of more pure science would be, you sit down and you have a guess, and then you come up with some explanation for what you expect to see, and then you can test that through experiment. Relativity, along with quantum mechanics and evolution, part of the big three. Okay, so these are the three most tested, most evidenced ideas in science: relativity, special relativity, and general relativity. Okay, so Galileo noted a number of things. But the things you just need to hold in the back of your head is that, one, he noticed that everything falls at the same speed. Okay, so heavy things don't fall faster than light things.
Is that right?
They all fall at exactly the same speed. So he hypothesized that a feather would fall at the same speed as a hammer. But obviously when you drop that, air gets in the way. So the feather does fall slower on Earth, but they did the experiment on the Moon on Apollo 15, I think.
Yeah.
Somebody will correct me if that's not correct. Apollo 15, let's say, and he dropped both a hammer and a feather on the Moon, and both fell at exactly the same rate. Okay, and that was something that Galileo noticed but didn't explain. Another thing that he noticed is that that things have movement in different directions. Okay, so if you fire a bullet, okay, it's got horizontal motion, but because of the Earth's gravity, it's also got vertical motion. So it's got, and the two are independent. So if you fire a bullet, the casing and the bullet both hit the ground at the same time. Okay, so it doesn't come from the horizontal movement isn't channeled towards the vertical movement. They're independent. Okay. Now, so these are just things you need to keep in the back of your head. Newton, obviously famous laws of motion, and he had a theory of relativity. And his idea of relativity was that all the laws in physics, okay, so all the physical laws, should be the same for all observers.
Okay.
Okay. So he said that you should, whether you're moving or you're standing still, the laws of physics shouldn't change. So F equals ma in a carriage or whatever they had would be true, and F equals ma on the roadside would be true. So it doesn't matter where you are or how fast you're moving. Yeah, the laws of physics are always the same. Okay, which is perfectly sensible and is true, but it's only part of a bigger picture. Okay, and then we have Michael Faraday. So Newton came up with these classical laws of mechanics. Things like the speed of something is, if you were in a car and you were throwing a tennis ball out of the car in the direction that the car's going, then the speed of the tennis ball is the speed of the car plus the speed that you throw it at. Okay?
Yeah.
So if you've got a gun and you're firing a bullet, the bullet comes out of the gun at a fixed speed. If you're driving and you fire a gun, then the speed of the car plus the speed of the bullet is the speed of the bullet compared with somebody, from the point of view of the observer. So Newton said that all of these things were correct. Then Michael Faraday.
So if I did a drive-by shooting.
Yeah.
And a couple of the homies did it from the car, but I stood by the car and fired, all things equal, same gun, same model, same bullet size, everything equal, same distance.
Yeah.
Only difference being the homies are spraying from the car, which is moving at 10 miles an hour, and I'm standing still. The bullet from the car will travel to its destination quicker than my bullet standing still.
That's right, because it's moving 10 miles an hour faster, assuming that you're both firing in the same direction, obviously.
Same target, everything's the same.
Same target, everything's the same. Okay, so they've got motion in that direction. You're also firing in that direction. So their bullet, the speed is the speed of the gun, the speed of the bullet plus the speed of the car. Okay. So if you were both standing next to each other, and he passed at 10 miles an hour, and when he passed you, you both fired, his bullet would get there before yours because it's moving quicker. Yeah.
True.
Yeah. So and this is what Newton worked out, and is very clever for doing so. And then we had Michael Faraday, who discovered elastic trickery.
Okay.
Electricity, I should say, and he did a lot of experiments and figured out that magnetism and electricity, moving charges, were related.
Okay.
Okay. And so you had this whole new part of physics. So before you just had Newtonian mechanics, which talks about how matter interacts with matter. Yeah. So when things bang into each other, what happens? Okay. And then you had this whole different thing of moving charges and magnetism, which are quite magical in comparison to general mechanics. So he didn't do a lot of formulation, so he didn't do a lot of maths, but did a lot of experiments. And then a guy came along called Maxwell, a Scottish chap, came along called Maxwell, and he formulated the equations for charge and magnetism, and he noticed that in comparison between the strength of magnetic force and the strength of the electrical force, he worked out that there was a speed limit that people noticed was exactly the same speed as the speed of light. Okay. Now, what was important about this is that it didn't matter how fast the experiment was moving. There was nothing in the equations that required you to state how fast the equipment was moving, and so this raised a conflict with Newton. Okay. So and what tends to happen is that well, in those days, what would happen is just say, well, Newton's right. Newton is Newton. It must be something wrong in Maxwell's formulation that's brought about this this difference between what Maxwell's saying and what Newton's saying. There's a conflict. So what you would do is what they tried to do was amend Maxwell's equations to match Newton's explanation of what was going on. And what they found was they couldn't. There was absolutely nothing that they could add to Maxwell's equations to make them both continue to explain Faraday's observations and also match what Newton was saying. So what they said was, well, this is really, really interesting, because what we could do is see how fast the Earth's moving. And two chaps called Michelson and Morley. So in testing what he was saying, what Maxwell was saying, which was, you know, that light has an actual speed; it's not instantaneous. So he compared the speed of the speed of forces. He compared the strength of forces and derived the speed of light from it. So what they could then do was experimentally, what they tested was the speed of light, and they said, right, well, what we could do is use the speed of light, measure it at midnight in one direction, then wait 12 hours so the Earth spun, measure it in the other direction, and what we should see is a shift. You know, it should be slightly faster in the direction that we're going, and slightly slower in the opposite direction, because the Earth's moving, isn't it? Yeah, and the speed of light plus the speed of the Earth will give you one speed, and then the speed of light minus the speed of the Earth, and you'll be able to work out how fast the Earth's going around the Sun. Yeah.
So can you actually put a measurable speed, let's say in miles per hour, on light, speed of light?
Yeah. So the speed of light is 300 million meters per second, roughly.
So 300 million.
So 3 times 10 to the 8 meters per second is how fast light travels.
And compare that to the speed of sound?
Speed of sound is 330 meters per second.
Wow.
Yeah, so quite a difference. Newton had it that light was travelled instantaneously. Yeah. But what Maxwell discovered was that no, that's not in fact true. So what they tried to do was to measure the speed of the Earth, because what they could then do is work out the speed of the Earth, which would contradict Newton's ideas about relativity, which is that you shouldn't be the physics, whether you're moving, there shouldn't be an experiment you can do that allows you to just see whether you're actually moving absolutely, or whether you're only ever moving in relative to other things. And that kind of makes sense, when you're talking about speed and you're talking about speed in a car. Yeah, you're sat having a cup of tea in the back of the car. You don't feel like you're moving relative to the car seat, but you are moving relative to the road. Yeah, so you have to look outside,
to realise you're moving.
To realise that you're moving, and what you're doing is saying, right, well, the road's not moving, so I'm moving relative to the road. So what they tried to do with the Michelson and Morley experiment was to measure the absolute speed of the Earth. Because they also believed in something called the ether, but you don't really need to worry too much about that. So they measured the speed of light, say midnight, and then 12 hours later in the same spot. So first they're measuring it in that direction, then through the 12 hours of the day, they're then measuring it in that direction. And they thought, well, we'll take one from the other and we'll work out the speed of the Earth. And what they found was there was no difference.
No difference.
No difference in the speed of light. So it didn't matter whether what it would be equivalent to is if you imagine a car driving past and throwing a tennis ball.
Yeah.
And then you throwing a tennis ball standing still, the speed of the tennis ball isn't changed by the fact that the car's moving along. Yeah, so Newton said, well, the speed of the tennis ball is the speed of the car plus the speed that you throw it. Yeah, with light, it was experimentally shown that it was always the same speed. So it didn't matter if so shining a torch from a car, the speed of the light coming out the torch isn't the speed of the light plus the speed of the car, which contradicts Newton, yeah?
That's quite a big contradiction. So if you go back in and say, look at my analogy, right, the drive-by shooting.
Yeah, so...
If you did a drive-by shooting and on top of the Uzi 9mm was a laser-guided a laser target.
Yeah.
So we've already established then that the bullet. So I'm by the car, you're in the car. You fire. The bullet is the car plus is the speed of the bullet plus the speed of the car.
Yeah.
So the bullet from me in a stationary position would hit the target slower. But if we both stood there with Uzi 9mm with the laser-guided targeting on it, the speed that those both hit the target would not be different.
It would be exactly the same.
It would be the same.
Yeah. So the speed, okay, the energy would not. You'd still get some sort of Doppler effect, but ignore that. That's not a problem. But yeah, so if you both turn torches on at the same time, okay, the light as he's flying past you, close to the speed of light, even. If you both shine torches at the same time, the light hits the wall at the same time. If you're firing bullets, then his bullets get there first. Okay.
Why? Why is that then?
Right, and this is the problem because you say what on earth is going on, and so this is what Einstein was thinking about, and he thought, right, so what it looks like is that the speed of light is constant. So it doesn't matter how fast you're going, whether you're traveling in a train, he used, or standing on the embankment looking into the train, you should always measure the speed of light as being 300 million meters per second.
Okay.
Okay, so it's a universal constant, the speed of light.
Mm-hmm.
Okay, so he then thought, right, well, what are some of the implications? What would it feel like to be traveling close to the speed of light? Because nothing can travel faster than the speed of light. But if I'm traveling at 99% the speed of light in a spaceship, okay, and I shine my torch inside the spaceship, well, there should be no experiment I can do that will tell me how fast I'm moving.
Okay.
Okay, so I should be able to shine this torch and still measure the light at 300 million meters per second, even though I'm traveling at, say, 298 million meters per second. So I'm traveling almost as fast as the speed of light. But every measurement I make inside the spaceship shouldn't tell me that I shouldn't be able to tell whether I'm moving at close to the speed of light or standing still, not moving.
Okay.
Yeah, and so that has some problems because you say, right, well, okay, so I've got my torch and I'm in my spaceship. I send my torchlight out of my torch, okay, and it hits off the wall, and I take very precise measurements, and I measure the speed of the light as 300 million meters per second. Okay. Now I've also accelerated my ship, so I felt the acceleration going all the way up to close to the speed of light. And so what must be happening in order for me to make measurements that allow me to come up with the answer of 300 million meters per second for the thing. And so what happens is that as you travel close to the speed of light, all the lengths shorten.
Okay.
So the distance, as I travel faster, the distance between myself and the wall that I'm shining my light onto shrinks. Okay, because this is the only way that you can take the measurement of the speed of light, which is distance over time. Okay, so that I get the answer 300 million divided by in 1 second.
Yeah.
Okay, and distance is shrinking in the direction of movement is something that has been seen. But imagine, and so from the outside in, looking into the spaceship. So inside the spaceship, you don't know that distances are shrinking. Yeah.
Mm-hmm.
You don't know. Because if you knew, then you could work out how fast you were going. So standing outside and watching the chap in the spaceship with his torch on, you know, I see the light coming out of his torch, and I've got to measure that light at the same speed as well. And so the distance dilation, the length dilation. So as things travel faster, they shrink. Okay.
So as things travel faster, they shrink.
In the direction of motion.
As things travel faster, they shrink.
Yeah.
Does that include solid matter?
That includes everything. Well, actually, what's happening is that space-time contracts. So the thing that this is going through. So they're not getting squashed. They're not going, oh, that's tight. The space-time that they exist in, which includes them, shrinks. So if you imagine a clock, this is the typical, the usual explanation that's given. If you imagine a clock that is just a light beam, okay, and it starts at the top and it goes boom, tick, 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 and it bounces off. And every time it hits the mirror, it ding dong, yeah, ding dong, and I measure the speed of that. And I work it out as being the speed of light, let's just say. Okay, so it's going the distance of the screen here, yeah? Mm-hmm. And we'll call it, now, if I'm moving and I do this, then by the time I've moved this direction, this far, then my clock moves from here to here, yeah? And so the light beam is actually going from here to here.
Okay.
Yeah? Do you see that?
Yeah.
Yeah, now this length, yeah, there, is more than that length.
Yeah.
Okay, but light always travels at the same speed, so we've got to work out that if the length goes from that to that, so through Pythagoras' theorem, okay, a squared plus b squared equals c squared, so a squared, that length, squared, plus that length squared, equals that length squared. So the square root of that squared plus that squared will give me that length. The main point to take away is that this length is bigger than that length. Mm-hmm. So me seeing you fly by, and I take my first measurement here, my second measurement there, my third measurement, and then I hear the tick when it hits here. Inside the spaceship, it's just going tick, 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 tick at the speed of light. Mm-hmm. But for the chap on the side watching, the light's traveling further, and it's not going tick, tick, tick. It's going tick, 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 compared to tick, 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 tick.
Gotcha.
Yeah, so it's going slower. Time slows down as you travel faster than the speed of light. That's complete nonsense. As you travel in space in a direction, time slows down. So moving clocks run slow. Yeah. So if you imagine the twin, this is called the twin paradox. Mm-hmm. Okay. And this is all, as I say, in order to preserve the fact that light must always be measured at the same speed. Mm-hmm. Yeah. It's always if it's always traveling at the same speed. So if length increases, yeah, then time is dilating. In order to maintain this time over distance over time equals the speed of light.
Okay.
Yeah. So time travel. So if you had a twin brother, okay, and you stayed down on Earth, and your twin brother got into a spaceship and he flew away, and he went in a big circle close to the speed of light. When he came back to you, you would be older than your twin brother.
Okay, that was going to be the question I was going to ask. Okay.
Yeah. So, and this happens. They've put an atomic clock in an aircraft, and they've they've synchronized 2 atomic clocks, put one on an aeroplane, flew that aeroplane round in a massive circle, brought it back down, and there's a time difference. Time differences are tiny, but because we can't really achieve super fast speeds. So there's length contraction in the direction of motion, and there's also time dilation. So that if you're I think a beam of light, from a beam of light's perspective, it only takes 80 years to cross the entire universe, whereas us standing still looking at the beam of light, then obviously it takes 28 billion years to get across the observable universe. So it's that kind of dilation. Okay, so you then say, right, well, imagine how do I move things forward? Okay, and you can use rockets or something, yeah? Now, in order for something to move in one direction, someone else has to move in the other direction, yeah? Because there's a principle called conservation of momentum. Which means, like, after you do some sort of change, the total momentum in that system stays the same. And momentum is mass times velocity. So it's just a combination of how heavy something is and how fast it's moving. So a P traveling at 30 miles an hour has less momentum than a juggernaut traveling at 30 miles an hour. So that when it hits, the exchange in momentum can either kill you instantly or just cause a P to hit your face and sting a little bit. Yeah. So momentum is the thing that's conserved. So if you think about it, right? So I'm in my spaceship and I'm traveling at 99% the speed of light, and then I add some more power and I go, yeah, I burn some more power, burn some more fuel to carry me moving. What's happening to that energy going in? Because I know that I can't travel faster than the speed of light, because nothing can travel faster than the speed of light. It's the only it's a constant in the universe. Nothing can travel faster than the speed of light. And what you find is actually happening is, it's absolutely correct. In order to preserve momentum, conserve momentum, but not break the speed limit, what is happening is that we're adding m times v, momentum, and that's being transferred into m times v, speed. What you find is you can never actually measure absolute speed. What you can do is measure transferred momentum. So as you add more energy in, that energy is converted to mass. So as things move, they get heavier. Yeah, so this is the other big implication. And the proportion to energy in and conversion to mass at the speed of light, with some jiggery pokery, you can derive E equals mc squared. So the energy in is just converted to mass at the speed of light. So if you fired more energy at that rate, so c squared is just the speed of light squared. It's just a constant. So energy equals mass. So at the speed of light, all the energy that you put in just gets converted into mass, and the thing just gets more and more massive. And because it gets more and more massive, it becomes more and more resistant to changes in velocity.
So what does it? So E equals mc squared is what?
E equals mc squared. So that's energy equals mass times the speed of light squared. Yeah. So and it's one of the products of special relativity.
Okay. So things only get heavier as they move if they're close to light speed.
No. So they get it's a square relationship. Yeah. So when you're traveling very, very slow, most of the energy in gets converted into velocity.
Okay.
When you're closer to the speed of light, most of the energy is going into mass, increasing the mass. Yeah. So if you imagine hitting a golf ball, okay, the energy going into that golf ball is mostly being transferred from the club. The momentum is hitting the ball, and momentum is always conserved. Yeah. So we know that m times v is happening at very low speeds. It's mostly it almost entirely goes into increasing the velocity of that golf ball. At close to the speed of light, it's the other way around. Most of the energy going into that golf ball is increasing the golf ball's mass.
Okay.
Yeah. So the faster something goes, the heavier it goes, the slower it ages, and the narrower it gets, if you like. Yeah. So these are all implications, and this is what Einstein figured out, was that if light is always the same speed for all observers, just thinking about, well, what happens if I was sat on a light beam and I tried to make myself go faster? What would happen to that energy if energy is always conserved and momentum is always conserved? And so we came up with a series of very simple equations for special relativity that just showed what happens when these things happen. And so since then, in things like particle physics, you've got particles that are traveling, that decay after a certain amount of time. Yeah. So there's a particle called a muon, and it only lives for the tiniest fraction of a second. But if you put it in a particle accelerator, yeah, and you spin it round, you know, close to the speed of light velocities, then it decays it lasts longer and gets heavier. So in the Large Hadron Collider and the smaller particle accelerators, what they had to do when they fire protons through this thing and it goes in a big circle, the magnetic fields you need in order to stop it crashing into the side of oh, my picture's gone. There we go. To stop it crashing into the sides of the ring are much stronger than the mass of the proton when it's standing still. So they had to increase the magnetic fields and strength to compensate for the fact that when you start moving things around very, very fast, close to the speed of light, all the energy you're putting into it, a lot of it's being converted just into mass, which of course heavier objects orbit at a, yeah. So all of these things have been, and of course the particle lasts longer. From the particle's perspective, say it does 20 orbits around the collider before it dies, yeah. If I'm stood outside, I still see it doing 20 orbits. Yeah. As I go around, and I still measure it, but I measure it as having a longer life, sorry, than if it was stood still. So from its perspective, it dies after, say, 20 attoseconds or whatever time it lasts. But I measure its time as longer. So what's actually happening is that space-time is warping in this bubble in order to allow all the measurements to equal out, which is quite weird. So from the, yeah, because it's got to do the same number of orbits, but in a different period of time, depending on its speed, from its own perspective and the perspective of its orbit. Slightly complicated, probably a bad example. But all of this is, and that's the special theory of relativity. Okay, so the idea behind it is that you should not be able to tell. Yeah, there should be no experiment you can do that allows you to detect there should be no experiment you can do that allows you to tell whether you're moving uniformly in the same direction at a constant speed, yeah, or standing still. So there's no experiment you can do if you're in deep space that could tell you whether you're moving or whether you're in one direction. Yeah, so we're not talking about curves and things, because that requires forces to act upon you. Yeah, so whether you're moving in a straight line in one direction at a constant velocity, or you're standing still. And additionally, the speed of light is constant for all observers. So combining those two ideas has all of these implications, which have all been tested in the real world experimentally. So the faster things go, they get heavier, they get more resistant to the change in velocity, so inertial mass and that. And then the time goes slower as you move. Okay, so the time goes slow as you move thing. If you think now, space-time is the thing that you then need to start thinking about. Yeah, and so space-time is a 4-dimensional thing. Okay, now if you think of a helicopter, okay, now it can either travel in a straight line like that, or it can go up.
Yeah.
And then the energy from the blades, the engine, okay, can either be put into going up, or it can be put into going forward. Okay. Now, so just in those dimensions, up and down and left and right dimensions. If you think about all movement in terms of time and movement, yeah. So as something moves, it can either move through the time dimension, or it can move through the space dimension. Okay, so something moving at the speed of light is moving really fast through the space dimension and not really moving that far at all in the time dimension. Do you see? So if it was a helicopter, it'd be very close to the ground and zipping along like that. If it's just sat there, then it's aging at its fastest possible rate. So it's not going through the space dimension at all very far, but is traveling really, really quick through the time dimension. And this is a constant speed for all objects in the universe. So everything in the universe is all traveling through space-time at the same speed. They're either going through it, and that speed is c. So they're either aging really, really quick, or they're moving really, really quick through space-time. Yeah, but if you plotted sort of the change through space-time of any object, whether it's light, which is massless, or people or elephants or whatever, you know, and so the twin paradox there, it's not really a paradox, but the twin sat on Earth is all of his speed is through time, so he's aging quicker. The guy who's going through space really, really quick, and he knows he's going through space really, really quick because he's subject to acceleration and then deceleration as he comes back down to land, so he knows it's him that's moving. He's zipping mostly through space, so he ages slower.
Okay.
Oh.
So
there we go. Yeah, so that's probably as far as you can go with special relativity. Do you want to know about general relativity?
Let's do it.
Let's do it. Boom! Right,
what I will ask though before you do this is thinking a little bit selfishly now.
Oh.
From the human race perspective, I mean.
Yeah.
Like, you know, given that I remember when I was a kid, right? And we're of a similar age, so I'm sure you are familiar with Star Wars.
Ah, the old Star Wars, yeah.
And the Millennium Falcon traveling at the speed of light and hitting light speeds.
Yeah.
Now, bearing in mind from telling me, I'm pretty much guessing that that's absolutely impossible. Why do we need to know all this stuff? What benefit is it for us to know all the wonderful things you've just explained? Okay, because it's of no benefit to it's not going to make us live better, or is it?
It is. So what the problem is that if time slows down, then what implications does that have for things like particle physics and things things like that you smash apart and you find the Higgs boson and you think, does this have any real world application? Well, maybe in the future it might. But one real problem that if you didn't know about relativity you'd have is you couldn't do things like GPS.
Okay.
Okay. Now, general relativity is analogous to special relativity in the way that so with special relativity you can't tell the difference between moving in a direction in a straight line at a constant velocity, yeah, and standing still. General relativity, Einstein looked at a principle of equivalence where he said you shouldn't be able to tell, there should be no experiment you can do to tell whether or not you're standing on a planet experiencing gravity or accelerating at 9 meters per second, that there should be some equivalence.
Okay.
To if you're going up in a lift, yeah, or if you're falling in a lift, if you go to Alton Towers and you go on one of these things where you a roller coaster and you come off the roller coaster and you just go into free fall, and you become weightless. So even though you're in a strong gravitational field, you fall at the same rate as your surroundings. Yeah. Okay. So you experience weightlessness, and that can be understood through changes in acceleration. So gravitation it causes you to change your acceleration, which is why it was always thought as a force. Okay. Now, so he said, right. So if it's true that you shouldn't be able to tell whether you're merely stood in a strong gravitational field or just being accelerated in a particular direction, and the speed of light cannot change, so and all that, then what that means is that space-time changes shape, and from that he then worked out that space-time was curved, and it also has problems in time dilation, for similar reasons of special relativity, and the maths is a lot more complicated for general relativity. But the point is that time progresses at a different rate according to speed, but also at a different rate caused by acceleration. Because if you think to yourself, if you're accelerating, then your speed changes. So all of the time dilation problems that we looked at in special relativity also apply in general relativity. So if you're being accelerated, then your speed is changing, and there shouldn't be a method of telling how fast you're going in absolute terms. So you get the same time dilation, but at an increasing rate, because it's acceleration is second order change in speed, second order change in position. So you get those problems. So in a gravitational field, time travels at a different rate. Now, if you want GPS to work, then on the Earth, time is traveling because gravity is stronger on the Earth's surface than however many miles up the GPS system works. Time travels at a different rate. So the clocks on the satellites have to run at a different speed than the clocks on the Earth. Okay. Otherwise, they can't work out how fast you're going or how your position has changed. And I think if they
that would be a pretty shit sat nav, wouldn't it?
Exactly, yeah. So if you didn't know about general relativity, you couldn't do GPS, because all the time you'd be like going, what on earth is happening? We've got these incredibly precise clocks on the satellite and on Earth, and yet they keep going out of sync. What on earth's happening? Okay. And so GPS is an implementation of general relativity. So you've got to adjust for the time difference, the fact that things in space age at a different rate. Time passes in space. Moving clocks run. Time on it. So the clocks in space run faster or slower. There's a difference. Anyway, I'm quite tired now. But moving clocks run slow. So, but then you're in a stronger field. So anyway, it would go out of sync, and you wouldn't be able to tell the distance. And rather than GPS being accurate within meters, it would only be accurate for a short period of time before it started going over kilometers. You wouldn't be able to tell your position. And that's how. And so what he then found out is that gravity isn't actually a force. There is no force of gravity. It's just the curvature of space-time around masses. So in order to explain how measurements made on the Earth and measurements made in space give you the same answers for the speed of light, there has to be a change in the shape of space-time. So, you know, in the direction of travel, it shrinks. Yeah. So for space-time in the general relativity is very curved. It's like a sheet, and things travel around. Now, if you think of, say, we go somewhere on the Earth's surface, just to kind of get this in your head of what this curvation, the curve is like. If we start on the Earth's surface and we walk parallel to one another and we head up to the North Pole, as we get close to the North Pole, we start to draw together.
Okay.
Yeah. Now, we might mistakenly believe that we're being pulled together by some mysterious force, and it's not. It's just the fact we're walking over a globe, which is a sphere.
Yeah.
So it's just a different geometry, and that's what the force of gravity actually is. It's just this change in the shape. So Earth is moving in a straight line. It's just space-time is curved by the sun. So it's moving, and light is the same. And so in 1919, I think, Arthur Eddington conducted an experiment that showed that the light next to the sun was bent by the sun's gravitational field during a total eclipse. So he took a picture with the sun not there of just the stars, and then when the sun was there during an eclipse, he took another picture, and the stars moved because the sun was there. So light was being affected by gravity in space-time, and that proved general relativity. So general relativity was a bit skipped over, I think, there. But yeah, so that is relativity.
Yeah, I think for a common thinking man such as myself, understanding the GPS analogy, I suppose, let's call
application.
Application.
Yeah, application general
helps me to understand it. Yeah.
Yeah. So and what scientists have, as they do with all theories, with evolution, with quantum mechanics and relativity, is to try and think of some really cunning experiment or cunning observation, try and find some bit of evidence that contradicts that theory, and they haven't yet.
Why would they want to contradict this theory?
Because that's how you make progress.
That's very true.
Yeah, so because I mean, with GPS, it matters whether or not we're right or wrong about general relativity, doesn't it? Because otherwise, you don't know where you are. So science progresses like that. So they try, somebody has an existing idea like Newton, and then they find through observation, they find some part of reality which seems not to obey those laws of motion. So what are the laws of motion? Newton's law of gravitation, what they noticed that Mercury didn't follow the correct orbit around the sun. Yeah, it processed, so the ellipse moved round over time around the sun, and they couldn't explain this because they accounted for all the masses and they couldn't really explain it. It wasn't till so you had an observation which contradicted the theory. Now in science, if reality contradicts the theory, you throw the theory out. Yeah, it's no longer a law of a physical law if it doesn't account for the things it claims to account for.
Yeah.
And so it wasn't until Einstein's formulation that accurately predicted the precession of Mercury, and so that showed that it was at least as good as, it was at least better than the last best theory, and that's all you can kind of hope for. You look at other ideas in religion and philosophy where people get so wedded to certain ideas, and then they see some observation, and what they don't do is throw away the idea. They don't go, this is a terrible idea, it doesn't match reality, and reality is king. Let's think of some reason why reality is wrong. Science can't work like that. You can't just stamp your feet and go, oh, but GPS should work without general relativity. It should just bloody work. It either works or it doesn't. And that's the strength of science. And the only way that it can do that is by scientists trying to make a name for themselves by disproving all these theories. Nobody's worked harder than science to try and disprove evolution, quantum mechanics, and relativity. But nobody's managed to do it yet.
Would you like to see the same application and commitment with regards to religion?
Where it matters, yes. Where it doesn't matter, I don't care. So, you know, so if you have, you look at MRSA.
Yeah.
Okay. So what's happening with MRSA is some tiny mutation in a population of bacteria in a hospital. Okay. Develops some mutation. Now, all of our antibiotics then kill off everything that's not immune to it, leaving just the MRSA bacteria, which then spreads through the population. You get a huge population of MRSA. And that, in a nutshell, is, although it's humans doing the selecting through antibiotics, but that is evolution by natural selection. So it's something that does happen, and it causes real-world problems. When you have, say, a religious person coming along and saying, yeah, that can't happen, well, that's fucking fantastically interesting. However, we do have this problem now that we then need to solve. Now, you can say, oh, it's because of gay marriage, and that's what's caused MRSA. You know,
as well as the floods.
As well as the floods. You know, the sin theory of disease as opposed to the germ theory of disease. You know, which is, and so you've got these two theories of disease there, and you say, right, well, how do we? That's, you know, you get to the point where you go, that's very interesting. Does it pass the so what test? Well, is it useful? Is it a useful explanation for what's happening? No, it's complete. The sin theory of disease is useless because it isn't true. So, no, you know, if you have a plague, you don't go around and tell everyone, well, you need to stop having extramarital affairs, and that will then cure the plague. Well, no, it won't, because what you're citing as the cause for that event isn't true. But rather than throwing that away, they then say, well, God works in mysterious way. Well, again, fucking fascinating. So what? You look at the germ theory of disease, or you look at any scientific theory about anything, and you say, right, well, how do I know that it's a good explanation? And you sort of say, right, well, does it explain what it says it's going to explain? Is the big one. Two, is it accurate? You know, is it predicting reality? Is it modeling reality? So that if I changed anything in that theory, it would either become right or wrong. Yeah, so it's very easy to change something in the theory and make it wrong. So if you take something like F equals ma, which is force equals mass times acceleration, which is a self-defining thing, but say I said, right, well, force equals mass times velocity, that would no longer be correct. It wouldn't explain reality. Yeah, you apply some force, and it's you apply force to a mass, and its acceleration, you know, its velocity changes, but not in a linear way, because force equals mass times acceleration, not force equals mass times velocity. So just an arbitrary change. So you look at some sort of explanation for the universe, and you say, God did it. You know, our explanation is God did it. Well, that's not that's a fucking fascinating, but again, useless. You know, if you change God to Thor, you don't change anything that it's explaining. So the God did it is not an explanation for anything. You know, if you said, well, where does the fine tuning from the universe come from? God did it, not an explanation, because if you look at the physical constants of the universe, let's say the strength of the strong nuclear force, and you say, right, well, God did it's the explanation. Well, how do I get from God did it to the value of the strong nuclear force? And if I tweaked it to Brian the Magical Unicorn did it, how does that change the value, the numerical value of the strong nuclear force? And of course it doesn't, because it isn't, one is not connected with the other. Whereas if it were, you know, you'd be able to do it. One of the problems, of course, is that we don't understand. Nobody understands where these values come from and how they change. And you can only model something once you understand it. If you understand it, you can model it. If you can model it, you can explain it. Okay, and that shows, we really understand general relativity because we can model it. We can program a satellite, and we can apply it. So general relativity is an extremely good theory for helping you find positions via satellite on a planet. Yeah, so it's a really useful thing. At no point do you go, therefore it's true. Do you know what I mean? You don't care whether you're tapping into some fundamental truth about the universe. You're only saying, does it work? Yes or no. If it doesn't work, get rid of it. If it does, yay!
Yeah, exactly.
Yeah, and that's how all knowledge and progress goes. You have a problem, you need to analyze that problem, you need to figure out what's happening in that problem and what it would take to solve that problem, and then you need to generate the solution to that problem. Sitting on your ass and going, well, I'm sure God will do something about it, probably won't get you, because the prayer theory of change is not a good theory of reality, it's not a good explanation of reality. So I think a lot of the religious types trying to hijack science and trying to get in the way and saying, well, we don't want progress. You can't. There's certain problems you're not allowed to solve because we interpret it as being some expression of Jesus's wrath or whatever. Yeah. Then that's not great. I mean, I've no problem with religious people saying, I love science and I want to find out more about the universe around me because I believe that Jesus made it and I want to know more about Jesus and things. Yeah, that's fine. Crack on. But what you can't do is subjugate reality to your religious belief, which probably only comes from where you're born. Do you mean if you're born in if you're born in Saudi Arabia, then you're probably going to be a Muslim, which means you're probably going to believe that this set of values is true. If you're born in South Carolina, you're probably going to be Christian, and you're probably going to believe that this set of values is true. Neither of those sets of values or beliefs about the universe come from some objective observing of reality. They come from just being told by your parents, yeah, this is true, that's not, this is good, that's bad. Now that's very interesting, but if you want to solve problems in the real world, they're going to be useless to you. So I don't have a problem with people going like, well, my religion teaches me to be good and loving to everybody, therefore I'm going to be good and loving to everybody. Brilliant, crack on. I'm all for you. Go for it. But don't stand up and say, well, my ignorance is just as good as your knowledge. Therefore, I want you to teach intelligent design in science class because I really, really, really believe it's true. No, go away. It's not even a theory. There's no explanation of going like, well, here's intelligent design, MRSA, and here's what we should do about it. And you look at the history of how we got to things like evolution and quantum mechanics. At each point, at each point in those theories, what happened next was predicted by the existing theory. So it's this really brilliant evolution, if you like, of each of those theories, which are good explanations for reality. Yeah. So, so yeah. I mean, these are all things that people should know and be aware of. And then, it can have social policy impacts, science. But I don't think it should work in the opposite direction. I don't think that science should be subject to the value judgments of people who have no understanding of it. Although, and that's not me saying it should be banned. That's me saying very few people are going to be interested in people's religious interpretation of science. You know, you're not going to convert anybody based on, you know, you're not going to convert somebody who knows how the Earth's age is calculated by saying, well, I've got a book and it says it's 6,000 years old. You know, that's not convincing. It's not a convincing means.
You're not convinced by Genesis?
No, and I don't think that's... I don't
Why?
think that should come
Why?
as a
There's no
surprise.
flaw in Genesis. It's flawless.
No, exactly. Yeah, I'm sure. But even if it were flawless, which it isn't, but even if it were, that's a claim. You still need, that's a claim about reality. You still need to test that claim against some model of reality to say, well, is this the way that the universe actually works? And of course, all observation shows that no, that's not how the universe works. And the story told here is incompatible with the understanding of reality over here. Again, not interested whether or not they think this is true or this is wrong. This method allows us to predict allows us to accurately model reality, so that when we make a prediction here, we do the experiment over here. The experiment occurs in along the lines predicted in the model, not along the lines of talking snakes and rib women.
So your theory is religion is basically bollocks.
It's not a theory. I think
religion is bollocks.
I think that when you have a claim about reality, which religion does, so all religions make very specific claims about reality. When observation shows those claims to be incorrect, you should throw those claims away. Not fret over it, not fight wars over it. Just go, right, clearly wrong. Because you need, in life, you need a method of figuring out what's good for you.
Yeah.
Of figuring out, only to your level of happiness, I suppose, figuring out. Now, with modern science and things like the NHS and things like that, it's possible to go through life and completely disagree with science. You know, if you hear the word science, mistrust and disagree, but they still go to hospital when they're ill. You know, they still go and buy food that has fat content below a certain level, because the explanation about why you get fat includes nutritional inputs. You know, that's a scientific theory. There's nothing in the Bible about that. So they like science when it's hidden and they don't really have to know about it. And then when they wake up after a 7-hour heart operation, they're sat there going, "Oh, thank you, Jesus, for saving me." Whatever. It wasn't actually Jesus that saved you. It was that doctor.
You can understand, though, or I can understand why a lot of people would be skeptical about science, particularly, and I'm not, by the way, I'm just speaking.
No, fine.
You can understand why people would be a little bit skeptical about science if part of what makes science science is the fact that it's all about trying to disprove the previous theory. So, you know, you turn around and say, for example, "Oh, I've done an experiment which shows us that," but then, you know, in a little laboratory somewhere, you've got actually working hard to disprove your theory.
Yeah.
The reality is, we don't really know. We're just constantly hypothesizing and trying to prove and testing and measuring, isn't it?
Yeah, exactly. And
so you can understand why someone with a strong religious view.
Okay, let's think about it this way. Okay, I design a car.
Yeah.
Okay, and I've got 2 cars, I should say. One car has been designed and built along the lines of advice written down in Bronze Age, in Bronze Age time in the Middle East, that tells you everything you need to be concerned about. So it's just a big engine, no brakes, because Jesus' will drive you. The other car is the product of testing until the thing fails, until each individual thing fails. And you test wanting to find the point at which it fails so that you can improve the design so that it doesn't fail. Yeah. Which car are you going to trust? Which car do you want to get into? One where you know the point at which each component fails, so you know how fast it can go, how hot it can get, you know, all of the physical realities, and built through the application of theory and engineering principles, so that, you know, you can be content that, you know, you're 99, assuming that you go at this speed on this type of road, you're 99% unlikely to have an accident or something. You can make an informed judgment on that. You know, which is what, when people say, you know, religion versus science, you're then going, well, which is the best car? Which is the best way to make a journey? And you've got people who'll drive the car made from science and say, yes, Jesus is my co-pilot. No, if Jesus was your co-pilot, you'd sit in the other car, the Bronze Age car, that wouldn't even start, and if it did, it would just explode. Do you know what I mean? So this want to test and challenge theories is to find, because the only way you can do it is to find out if it's wrong. If you want to know if it's wrong, so you say, right, well, if this theory says I can travel faster than the speed of light, that would be a very useful thing if it were true. So you say, well, that's a really interesting theory. Is it true? It doesn't get anywhere closer to being true by not testing it. So you test it and you test it and you test it. And if you test things in circumstances that the theory says should work, yeah. So, for example, the Higgs boson, which is a particle, before it was discovered, it had a range of energies. So the theory said it's somewhere between this point and this point. And all the colliders and particle accelerators that we had could only measure up to here. Yeah. So when the Large Hadron Collider was built, which can measure energies up to here, say, if it's up to here and doesn't find the Higgs boson, then that would completely overturn the Standard Model, which is a fundamental theory of physics, you know, really, really important. So having this piece of equipment, and if it found it, brilliant, confirmed the Standard Model. If it didn't find it, brilliant, tells us something else that we didn't already know. So in order to, in trying to find this particle and confirm whether or not the Higgs mechanism was real, you know, either way, whether you're right or wrong, it's going to be interesting. Do you know what I mean? But you get there by trying to say, right, well, let's find the situation where it should appear, and if it doesn't, then we've caused the theory to be overturned, which means you go and think of a different theory.
So would you be happier if religious people took more of that kind of stance? God exists, or Jesus did this, but let's prove that he didn't first.
No, I mean, there's certain things that aren't really open to examination. So you might have heard of the thing that some theories aren't even wrong. So they're theories about the world that say nothing. You know, they say nothing about the world. So when you say God did it, it isn't a theory. It isn't a scientific theory to say God did it, because it says nothing about the thing it claims to talk about. Yeah. So if you said, well, God makes it so that the sky is blue, yeah, then you get a bit closer to you can judge. Well, is the sky blue? You know what I mean? You can find you can look at, is the sky blue? And what you see is that, well, sometimes it's blue, and then sometimes it's not blue. And so you then get into this thing of like, well, what causes the color of the sky to change, or what are the variables? So when we notice that the sky's blue, where's the light coming from? You know, when we notice it's red, where's the light coming from? And what you see is that it's the angle of the light incident on the atmosphere that seems to have the biggest impact on color of atmosphere. So what you've shown there is that the color of the sky is linked entirely to the angle of the light that's hitting it. So if you then want to maintain that it's God doing that, yeah, then you need to think of an explanation that, if you took God away, would change the color of the light. Yeah, so God did it is not a good theory for anything. But what you're not saying is, well, it's not, because then you say, well, who is it that makes the light go at a different angle? Oh, that's God. And this is what they do, is you sort of explain this, and then they say, yeah. Well, it's God that's making is the bigger thing, and that's why God did it now tends to be only linked now with things that we don't know about. So what happened before the Big Bang? Yeah, because science does not have a model. Well, there's a few, but there's no sort of scientific there's no experiment you can currently do that will allow you to look back before the Big Bang, because space-time was created at the Big Bang. Yeah, so you hear it a lot then. They'll say, yeah, God did it. Because there is no other theory. So they just go, yeah, God did it. Another one is, does free will exist? God did it. There's no scientific explanation for consciousness or free will. Okay, at the moment. Free will may not even exist. Yeah? So they'll say, God did it. Quantum mechanics. I don't really understand quantum mechanics, therefore God did it. And there's lots of things like that. And then God becomes this, as Neil deGrasse Tyson says, this ever-receding boundary of scientific ignorance. So as science sort of gets rid of it as an explanation. But at no point has anybody gone out and tried to disprove God. Because the theory God did it isn't even a theory. It isn't even wrong. Because it says nothing about there's nothing it's saying about it. You know, it's like saying, yeah, there's an invisible troll next to you, and you can't see it and you can't detect it. Prove it wrong. Otherwise it's true. Do you know what I mean? You just go and go, well, no, I'm just not going to believe it. You prove to me that it's there, and then we can talk. But I can't prove that something I cannot see, hear, or detect is there.
Can you imagine the hopelessness, though, for a lot of people, that if it was proved that God didn't exist?
Well, what is purpose? You know, people want purpose. That's the cry for a slave master. I need somebody to tell me that I'm doing well. I need somebody to give my life purpose. You give your own life purpose.
Do you know what? For me personally, and I'm not a religious man either, but it's not about life purpose. It's about what happens after.
Right. So religion says that certain things happen afterwards.
Well, imagine you're in a scenario where, you just believe that you're born, you do stuff, you do something, and then you die, and that's it.
Yeah.
You can understand why people have that. Yeah, we go to a better mentality, because it creates hope, doesn't it?
Well, I think that the want to improve your situation is admirable and very good. I think it's bad if you say, well, there's nothing you can do in the real world, so just wait until you're dead. Do you know what I mean? And then things will suddenly get better for you.
That is ignorance, isn't it? It's like,
can't I just have something now?
I'm not going to take my chances now. I'm not going to take my chances now. I'm not going to try and better my life. All I'm going to do is help old ladies across the road, and one day I'll be in paradise. Exactly,
yeah. And I think the idea that, everyone's just muddling through, because you hear the argument, well, if you're not doing it, if there's no universal pet owner that pat you on the head and tell you you're doing well, what's the point in being good? Being good is hard. Following the rules is hard. Why should I bother if there's no reward? And then from that, you just got to think, well, so what you're saying is the only reason you're nice is because you think you're going to get rewarded. That doesn't make you a nice person. That makes you a very selfish person.
God, mate, that's a really interesting way to look at it. So, even the reason that people follow these values set out in the Bible is, if you follow these values, you will go to heaven. So people are only not murdering each other and coveting thy neighbour's wife.
Exactly. I mean, it's
purely because there's this promise of a greater afterlife.
That the benefits from stealing are going to be outweighed by the benefits of going to heaven. Now, I think it's offensive to say that, the Israelites, let's imagine for a minute that the Exodus actually happened. Are we really saying that the Israelites, until Moses came down off the mountain, didn't realize that murder was wrong? Didn't realize that stealing was wrong? Well, of course they did, because if you look at the story of Moses, he was brought up in the Pharaoh's palace, and he saw a woman being beaten by a slave driver, and so he killed the slave driver.
Yeah.
Now, rather than standing around and going, well, I did nothing wrong. Murder isn't bad. Murder isn't banned. You know, God has never told us not to murder. No, he runs away. You know what I mean? So he knew it was wrong. So it's ridiculous for him to go up the mountain and only then find out that it's wrong to murder. You know, so I mean, one of the many nonsense parts of the Bible is this idea that we get right and wrong from the Bible, that we get morality from the Bible. We don't. You know, there are things in the Bible that we condemn now. So things in the Bible that they say, this is how you should treat women. This is how you should treat your daughter if they do X, Y, and Z. We would say, no, that's completely unacceptable. And if you actually do those things, we'll put you in prison. We will cause you to suffer. You know, so we're obviously not getting our morality from the Bible. We're testing the Bible against our own ideas about morality. And where it falls short, we say it falls short. Do not do these things. Because we've got the idea of the harm principle now, where we say, well, an act is either, you know, bad or good or morally neutral. So you can do things so long as you don't cause harm to other people. We have no interest. If you want to go home and cover yourself in barbecue sauce and roll around on teddy bears, crack on. We're not.
You're still into that.
Yeah, right. just at Christmas and Easter.
You don't mind on the internet. That's good, man. You're a strong character.
Yeah. So we, from that point of view, you know, you've only got your own. And I think this is the thing: when you realise that nobody is in control. There is no God. There is nothing out there telling you you can and can't do something. Then I think for a lot of people that's very liberating. I think for people who spent their entire lives on their knees, you know, telling everybody they're unworthy whilst at the same time condemning everybody else, I can understand the Concorde effect. You know, I can't turn back now. I've got to keep saying I believe in God. I can understand that, you know, being proved wrong is hard. You know, even for scientists, you know, you pay lip service to saying, well, I'm open to have my mind changed, but when it happens, it's not nice. Yeah, I get it that people don't want to change their minds, but I think it's incredibly liberating if you just say, and even if you don't, you've got to think to yourself, well, what's better, sincere disbelief or pretended belief? Do you know what I mean? And one of the problems I've always had is this idea of faith as being a virtue. So just take my word for it. And you say, no, I'm not going to take your word for it. I mean, you think in the business world, imagine that there was a God of the business world. And people, if you were doing something other than what this guy said, you were doing business bad. Doesn't matter whether it caused your share price to go up. Doesn't matter if it caused your customers to get the things that they need. Doesn't matter that that through research and development expenditure you come up with a cure for cancer, driven by the want to increase shareholder wealth and a cooperative. It doesn't matter if any of that happens. It only matters whether or not you do what it says in the God of Business book. And at which point you go, well, actually, I'm not interested in that. What that says is irrelevant. That is not, to assume, because then if you get rid of the rule book and you do things that make your business grow and that get your customers what they need, then that's good enough, isn't it? You don't then say, but my business has no purpose. Do you know what I mean? You don't go, I'm not pleasing the God of business. It therefore is bad. Or it therefore, how dare we throw away the God of Business rule book, because that's where all of our rules of business come. No, you try something, does it work? Yes or no? If the answer is no, throw it away. Think up something new.
Yeah, that's very true. Do you know what, Darren, I've got to say, it is unfortunate that I have a conference call at 2 o'clock.
Oh, Danny. That's okay.
But can we do this again, man? And I'd like to get into this subject, because this is.
That's fine.
I knew that when we discussed this earlier on today, I knew that it would be a fascinating insight, because in all the years I've known you, and I haven't seen you for many of them.
I know, it's ridiculous, isn't it?
You always were a very profound, articulate, intelligent man, and you always, even if I thought you were talking absolute bollocks,
you believe it anyway. I should have my own religion.
It's the way you articulated it. It's like, yeah, you know, I could sit here now and say I am a devout religious man, but when I speak for an hour and a half, he's got me questioning stuff, and that's good.
Yeah, I mean, if it's true, it's not going to fail questioning. Do you know what I mean? This is the thing. If it's a theory which gives you some direction in life, you know, I'm not going to go up to an old lady who's just buried her husband and shake her and say, "There's no God." But if you're trying to achieve something in the real world, then you need to be at least aware of how the real world actually works. Otherwise, you'll fail.
Yeah.
And that's, you know, separate them in your mind if you wish. Have them as different things, but always have a care for what it is you're actually trying to achieve, rather than trying to please something which, you know, in many cases is ill-defined.
And probably non-existent.
And almost certainly non-existent. But yeah, anyway, I will let you go and have your conference call.
Appreciate that, mate. Absolute pleasure.
That's okay, and always good to talk to you.
I got some notes. I've made notes, like, just to prove that I have been listening to you, and I've not just been going I have.
Look at those notes. Excellent.
At least 4 pages of notes, and stuff that I'm going to go and.
Well, I would say, do not take my word for any of that. This is the thing with science. Don't take my word for it. Go and look it up.
What you've done is given me a fascinating insight and foundation into something I literally know fuck all about, and now I know a little bit more than I did. And
a little bit of knowledge,
little bit, yeah. But you've given me references and things that I can look up and learn more about, which for me is my own progress.
Exactly.
I am my own project of evolution.
Well, not quite. The current understanding of evolution is that you're frozen at conception in terms of your genetic makeup. So short of, you know, some sort of gene therapy that you might devise, some evil gene therapy, I imagine, with you, your genetics are kind of fixed. So if you want to evolve, have some children.
Good plan.
Yeah. Anyway,
mate, brilliant. Thank you, Darren. Let's do this again, can we?
We will, of course we will.
Cool. I'll Facebook you later.
I'll speak to you later. Take care.
See you, mate.
Bye.
Bye.